Let's do a problem which was assigned in test number 1. So the problem says something like this. Assume x is a real number such that x cubed is a rational number and x to the power 5 is a rational number. Prove that x is a rational. Oh. So it's important to, before beginning the proof, to discuss two small useful lemmas. So product of two rational numbers is rational. Indeed, if you multiply a quotient of two integers by another quotient of two integers r over rs, where p, q, r, s are integers, and q and s are not zero, the product will be pr over qs, which belongs to q. Then quotient of two rational numbers with a denominator not being zero, the quotient x over y, where x, y belongs to q and y is not zero, is rational. Indeed, if we divide p over q by another rational number r over s, where r and s, so that to make sure that r over s is a non-zero rational number, r over s are both non-zero. Now, this quotient will be ps over qr is non-zero here, and belongs to q. So these are useful, two useful things which are instrumental in solving the problem. Okay, so first of all, let's try to go to eliminate a trivial case. So if x equals to 0, there is nothing to prove. So see to state it because we'll move on with x non-zero. There is nothing to prove. Because 0 is rational. So this being said, let now x not be 0. Let's assume the two premises. So with x cubed and x to the power 5 rational number. Then, if we divide, how can we get x to be rational? Well, try to find a mathematical combination of x cubed and x to the power 5 producing x. It's very easy to notice that it's x cubed to the power 2 over x to the power 5. So it's clear that we can divide by x to the power 5 as long as x is not 0, and then x cubed is a rational number, the square of x cubed is a rational number, defining a rational number over x to the power 5 is irrational, it will be a rational number. So therefore we prove that x is rational. How can we generalize this? Let's try to put it in this way. Assume A and B are positive integers. The following are equivalent. First, A and B are relatively prime. So greatest common divisor of A and B equals to 1. In other words, A and B have no common factor no positive common factor other than 1. 2, for every real number x, if x to the power A and x to the power B are rational numbers, then x is also rational. As always, to prove an equivalence, we have to prove the two implications. One implies two, and then two implies one. Let's try to prove first one implies two. So again, let's assume that the greatest common divisor of A and B equals to 1. So say GCG of A and B equals to 1. And then assume that x to the power A and x to the power B are rational. How can we prove out of this that x is rational? Again, as before, we may assume, or we just say if x equals to 0, nothing to prove. So, we want to prove, so we want, I'm going to put it here, we want x belongs to 0. So, if x equals to 0, nothing to prove. Let x not be equal to 0. Okay, now, a very important statement, consequence of the fact that the greatest common divisor of the integers A and B is 1 is that there is a integer combination of A and B which produces 1. So let K and L be two integers such that AK plus BL equals to 1. The existence of those numbers K and L is guaranteed by extended Euclidean algorithm, as a consequence of the extended Euclidean algorithm. Okay. So let's try to get some space here. So what do we have here? X to the power A is rational. X to the power B is rational. KA plus LB equals to 1 because the greatest common divisor of the integers A and B is 1. And also x not equal to 0. How can we generate an x out of a combination of those numbers? X will be x to the power KA plus LB. This will be x to the power A, everything to the power K, times a to the power B everything to the power n. Well, for example, one of the numbers k, L could be is positive, the other one is negative, so that we can, in here, this product actually is a quotient. Now, because x to the power a is a rational number, any power of a rational is rational, so this is rational. And this is rational. This product slash quotient of rational numbers is rational number. So let's take an example, concrete example. I just wrote one concrete example, numerical example. X to the power 7,211 is rational number, and x to the power 5,112 is a rational number. So from these two, after applying the extended Euclidean algorithm, we'll get x equals to x to the power 7211 everything to the power 2075 divided by x to the power 5,112 everything to the power 2,927. That's exactly x. So because GCD of 7,211 and 5,112 equals to 1 allows us to write by, after extending the algorithm, to write 1 equals to 7,211 times 2,075 plus 5,112 times minus 2927. So you get the balance of those numbers A and B, which produces the greatest common divisor. And of course, we already know that we eliminate the trivial case x is not 0. So x belongs to x rational number anyway. Okay. Let's do the reverse. So far we proved the implication is 1 implies 2. So in other words, the GCD of A and B equals to 1 implies for every x in R, if x to the power A is a rational number and x to the power B is a rational number, then x is a rational number. To complete the problem, so we can prove 3 implies 1, or we can prove the negation of 1 implies the negation of 2. So in other words, GCD of A and B greater than 1 implies there exists an irrational number x with x to the power A and x to the power B both rational. So if the greatest common divisor of A and B greater than 1, then we have to show that there exists an irrational number x such that x to the power A and both powers x to the power A, x to the power B are rational. This again is trivial. So let's assume, so let's start from this one. If the greatest common divisor is bigger than 1, let's pick up a divisor, a common divisor of A and B, which is greater than 1. Let's say B, a positive integer, is a common divisor, so bigger than 1. A positive integer uh, bigger than 1 is a common divisor of A and B. So B divides A and B divides B. Then, for this x, we can take the example root of order b of 2. And we already did this in class with other examples, like with cube root of 2, we prove the square root of 2 is irrational, and then cube root of 2 is irrational. And in the same way, we can prove that any subsequent root of 2 is irrational. But x to the power a, because a is a multiple of d, so is cube d root of 2 to the power dA prime, because A being the multiple of B can be written as A equals to D times A prime, where A prime is some integer. And this will be 2 to the power A prime, which is a rational number, which is a rational number. And x to the power B equals to root of order B of 2 to the power B, which will be dB prime of B4, with B prime some integer, which will be 2 to the power B prime, again, a rational number. So, to summarize, if the greatest common divisor of A and B is greater than 1, then we can find a real number x, which is irrational, such that the x to the power A and x to the power B are both rational. And this kind of completes the generalization of the problem in the case number 1.